So welcome everybody. My name is Alex Razumov. I'm a visualization coordinator for WestGrid in Western Canada. I'm based in Vancouver, and I'll have a presentation. So today's presentation is going to be fairly introductory. I'm going to cover the main items. We'll describe our visualization support in general, how you can get help, and what you can do in terms of visualization in Compute Canada. And then I'll run several demos live on my laptop, sharing the screen, and then we'll talk about remote visualization. And finally, I'll talk about our training and things we plan for these future webinars. So my email address is alex.razumov@westgrid.ca. At any point during the talk or after the presentation, you can send me questions, your feedback, and so on. So you can download a copy of these slides. I put a link here on the title page. It's bit.ly/WG for WestGrid, CC for Compute Canada, V for visualization. So if you go to that link in your browser, it will download a PDF, which will be exact copy of the slides I'm going to show today. So a lot of researchers in Compute Canada are running large numerical simulations, and they have large data sets that they need to analyze and visualize. Perhaps you might also have some experimental data, and you need to visualize this data. So we're going to help with all aspects of visualization. We have a technical team of about half a dozen people across the country who can provide help with visualization. So if you are in WestGrid, one of the WestGrid member institutions, just feel free to contact me. My email address is on the title page, or simply send a support email to support@westgrid.ca, and your request will go automatically to our ticketing system, and I will try to answer your question as soon as I can. So in other consortia, SciNet, SharkNet, Quebec, AceNet, and the Center for Advanced Computations at Queen's, you can send an email to their equivalent email addresses for support, so you probably know the exact emails of those. You can also send an email to wes-support@computecan.ca. So this is a mailing list that is monitored by all consortia, and most likely somebody will be able to answer you within an hour, maybe a couple of hours. So also for the past few years, we had a checkbox need visualization help in the RAG applications. So as you probably know, every fall, if you require a lot of computing resources beyond what is provided by the default queues, you can submit an application for resources. And in the application form, there is a checkbox that you can mark. If we see that you indicated that you need help, then we'll contact you at the beginning of the year, and we'll try to help you with visualization. So to see the examples of visualizations people do in Compute Canada, you can follow this link. So bit.ly/cc/top-vis. Let me just open it on my laptop. And so here we have a quick introduction to the visualization team and about a dozen of different examples. So you can click on these individual examples, and it will show either an image or a movie, a little bit more information about the visualization. So most of these were done with three-dimensional visualization packages. For example, this visualization of a galaxy formation model was done with Triview. So in this case, it's a very small run, 12 million particles. But the problem was that to visualize it, actually I had to, well, I wrote a script to port the data to a three-dimensional unstructured mesh, and then I did volumetric rendering of the mesh, so you can actually play back this movie. I'll show some nice spinning effect. And if you scroll down in this page, there are a little bit more information on how exactly this visualization was put together. You can click on other examples as well, just to get an idea of what kind of three-dimensional visualization people do in Compute Canada. So for more detailed documentation, we have a wiki page, which is linked here at the bottom, docs.computecanada.ca. And there we have a lot more information. So most importantly, we have information on various regional visualization pages. So details on how to do visualization, remote visualization on the clusters in different consortia, in different regions vary. And I'll be talking a little bit more about this in this presentation. But if you want to get more details, then you can click on these individual links. So we have links for WestGrid, for SciNet, and for SharkNet, and AceNet, and Quebec don't really have any special visualization pages. So also we have some presentation materials. So I'll talk about these more furthering this presentation. We run full-day visualization workshops, either covering Triview or Visit, and we have full slides from these presentations. Also, we have slides from various webinars and so on. So there's quite a lot of materials you can find useful on this page. Primarily, we try to use three-dimensional open source tools for visualization, such as Triview, Visit, VTK, Visual Molecular Dynamics, VMD, various Python three-dimensional libraries, as opposed to closed source or proprietary or commercial tools. So the problem with commercial tools is that well, you need a license to run them even on your desktop, and sometimes, very often, these licenses are quite expensive, and you cannot also scale easily to much larger computational resources. So, for example, we have with MATLAB, we have a limited number of in WestGrid, a limited number of licenses that you can use, but if all licenses are in use, then well, you are out of luck. So I know some researchers, quite a large number of researchers, use proprietary packages such as MATLAB, IDL, Interactive Data Language, and so on. So we'll try, if you need help with one of these commercial packages for visualization, we will try to help you as much as we can, but obviously we'll be limited in what we can do, because, for example, I don't have a desktop license for either MATLAB or IDL, and so I'll try to help you get started, but I probably won't be able to run MATLAB or IDL scripts myself. Whereas with open source packages, we don't have any such limitations. So we can run them anywhere, on any cluster, on any desktop, and we can scale to many number of processes and so on. So if you need to import data into one of these packages, it's fairly easy to do if your data set is one of the standard formats such as NetCDF, HDF5, or it comes from a popular simulation package. If the visualization program cannot import your data set, we'll help you to write a converter, or perhaps to write your simulation code, or perhaps to write a plugin, a reader plugin for one of these packages. So we can make sure that you can read your data in one of these tools. So the only difficulty will be if you're using one of the commercial packages, closed source packages, and if we don't know the specification of the data set, so we see an output file, which is some binary file. In that case, it might be problematic to read it into one of the open source tools, because, well, we don't know the specifications. Sometimes we can actually reverse engineer the binary file. So a few months ago, I did it for a particle output of fluid, where we could actually try different things, and we could guess the format, the exact particle storage format that Fluent uses. But sometimes it can be difficult. So, and so finally, what I want to say on this slide is that if you have a very large data set, then you can visualize it directly on one of our clusters. And obvious benefit of visualizing directly on a cluster is that you don't have to download a very large data set to your machine. And obviously the resources on a cluster, so CPUs, and well, we'll have many more CPUs and nodes for visualization, and you will also have fairly fast GPU cards. So if your data set is very large, so you cannot visualize it or even fit on your laptop, you can try visualization on one of our larger machines. So a couple of notes about our visualization events. We run, for the past few years, we've been running a Seeing Big showcase. So the idea here is that for 3 months, from early March to end of May, we're accepting submissions from researchers. So asking researchers to submit either static images or even better, videos of their visualizations. So the idea is that researchers can actually advertise and showcase their own research. And these submissions will be incorporated into a 4K movie, which is going to be played in the lobby on a 4K display in the lobby of HPCS. So HPCS is an annual supercomputing conference in Canada. All Canadian Supercomputing Conference stands for High Performance Computing Symposium. And this year in June is going to be at Queen's University in Kingston, Ontario. And we'll be accepting submissions starting from early March. We'll be accepting submissions for these. So typically a couple of dozen research groups participate, submit their work, and we end up with a half-hour to an hour 4K movie that is played in a loop in the lobby of the conference, so everybody can actually see it very easily. And so we're looking for wide participation in 2017, and we'll probably sometime in February, we'll send an email to all Compute Canada users asking you to submit your visualizations. So since last fall, since 2016, we also started running another event in the fall. visualize this competition. So the idea here is that unlike the previous event, unlike the showcase where researchers have been their own visualizations, in the challenge, we ask researchers to work, primarily postdocs and grad students, to work on on the same data set. So everybody's working on exactly the same problem, the same data set, and it is a competition. So we have prizes, and the best visualization will win the prize or several prizes. And the idea here is we try to advertise, first of all, visualization, advertise different visualization packages and different ways to visualize data. And we try to come up with a problem that is interesting and accessible to everybody. So not some very specialized field, but something that many people can understand and relate to. So for example, last year, we had an oceanography model from a global ocean, full Earth ocean simulation. And we zoomed in on two regions, one in Northern Atlantic, the other one in Pacific. So we had data for various currents, for temperature, for salinity, and a few other variables. And we asked researchers to visualize this three-dimensional data set. So the winner of that competition was a team from the computer science department at the University of Calgary. And they won the top prize, which is a free trip to HBCS. And they're going to present a talk in one of the sessions at HBCS in June. And so we're thinking we might have a separate visualization session at HBCS in June, maybe. So we haven't decided yet, but we're still planning this, and we are accepting ideas for a session. So one possible topic for this session could be visualizing scientific visualization in augmented reality and virtual reality. So this is something that a lot of virtual reality headsets have been coming online in the past year or so. And it'll be interesting to see how people actually use it for a scientific visualization. So if you have any suggestions for a theme, for a topic, for a visualization session at HBCS, then please let us know, and we'll discuss it with you. All right. So there are lots and lots of huge number of three-dimensional, two-dimensional visualization packages. So in 2D, if you do big data analytics, visual analytics, I'm sure you've heard of lots and lots of packages. So a lot of them are derivatives from D3GS, JavaScript library, really dozens, if not hundreds, of different visualization packages. There are scientific visualization packages that do things like matplotlib, gnuplot, bokeh, many others. And we're happy to support all of these two-dimensional packages, but it's actually fairly easy to use two-dimensional packages, because usually if you go to to a web page for one of these tools, say matplotlib, just click on the gallery link and it will give you lots of examples, and then you click on an individual example, and it will give you the Python source code behind that example, so you can actually adapt it to your problem and do things quite easily in 2D. So three-dimensional visualization is obviously a little bit more complex because you're dealing with larger data sets, and also rendering times might not be small. So you can actually take some time, CPU time or GPU time to do actual rendering. So there are a number of really, really good open source three-dimensional visualization tools. So some of them are domain or task specific, like the ones listed here. So we can help with all of this. But when we do training, we try to steer researchers towards a couple of really, really good three-dimensional open source visualization packages. One of them is called Triview. The other one is called Visit. And these tools are specifically written for visualization of very large scale data sets, and they're general purpose tools, and they're not limited to, let's say, molecular dynamics or astrophysics or just one particular field of science, but they're meant for visualizing pretty much any data set, any spatially distributed data set. And they're really powerful, and we know these tools very well, so we can help you with all aspects of visualization, from writing scripts to remote visualization and so on. So just to go through the capabilities of Triview and Visit. They've been written specifically, as I said, with the idea of visualizing very, very large, gigabyte and terabyte size data sets. So they can visualize pretty much any type of data, scalar, vector, tensor fields, or something else, defined on any type of spatial grid. So it could be a regular Cartesian grid, it could be an unstructured mesh, it could be particles, it could be some very strange irregular topology, whatever, as long as it's some sort of spatial discretization. And then you have variables, scalars or vectors or whatever, defined on top of the spatial discretization. And so these tools are open source. They can run on pretty much any platform, Windows, Linux, Mac. and you can download them as open source. You can download as precompiled binary. You can easily run them on your laptop, but they can also scale to thousands of processes to process very large data sets. And by large, I mean from hundreds of megabytes to gigabytes and even terabytes in size. So obviously, if you want to analyze terabyte-sized data set, you cannot do that on a single machine. You have to do it in parallel. And both of these tools can actually scale to thousands of processes fairly easily. And they support a huge number of input file formats. They let you do things interactively, just sit in front of a client and do things, or you can script them in Python. And they're really, really powerful. They can do pretty much anything you can think of. And so they provide a huge number of, both of them have over 100 different visualization modes or filters or operators. They use, so for heavy-duty rendering, they use OpenGL for hardware acceleration. But if you don't have a machine with an OpenGL card, with a GPU card, you can also run run both of them purely on CPU. So they have a number of software-based ray tracers and rasterizers. So you can actually run it on, let's say, a cluster node that doesn't have any GPUs, and you can still do some efficient rendering. So both of them support in-situ visualization. In-situ visualization means changing your simulation code so that it outputs not the raw data set, but something that can talk back to a Triview or a visit client. And you can actually run a simulation, and at the same time, while the simulation is running somewhere on a supercomputer, in Commute Canada, you can run a Triview or visit client, and from the client you connect to the simulation live, and you can actually look at the results, and you can there are mechanisms for steering your simulation, so you can modify some things and while the simulation is running. So it's really, really powerful. And there are some other capabilities. So for example, instead of outputting the full data set, you can output only things that are required for visualizing a specific variable. So let's say in advance you know that, let's say you're doing a fluid dynamic simulation, and in your fluid dynamic simulation, you know that all you want to do is visualize, let's say, isosurfaces of some variable. Then you can output only data that is required for visualizing the isosurfaces of this variable, as opposed to the full data set. And so this reduced data set will be much smaller in size. It'll be much easier to save it and to manage and to visualize it than the full original data set. And both tools, both Triview and Visit, are built on top of VTK, which is a visualization toolkit. So it's a popular library that's been around since the early 1990s. It's a popular computer graphics library, so it has lots and lots of useful stuff, lots of built-in functions for visualizing, isosurfaces, or doing volumetric rendering, and lots of different things. So both Triview and Visit can interface very nicely with VTK and can understand all VTK file formats. So what I'm going to do next, I'm going to run a couple of demos. First, I'm going to run a Triview demo and then a Visit demo. And for each of these applications, I'm going to run them on my laptop. And for each one of them, I'm going to load a data set. It's going to be the same data set for both packages. I'm going to do some interactive visualization, and then I will load a more complex visualization stored in a state file, a session file. And then I will do some scripting. I will actually copy and paste a script I wrote before into the built-in Python shell, and we'll show you how to run scripts in both Triview and Visit. So let me start first with Triview. Let me start it on my laptop. Okay, I'm going to open the file, so I'm going to navigate to the directory that contains the dataset. So the dataset I'm going to load is called noise.silo, and it's actually a dataset that comes with Visit. So even though I'm running Triview right now, it's a dataset that's standard with every Visit installation. And I'm using it even with Triview simply because it's a very nice three-dimensional dataset that has some not exactly random, but kind of random data. And I just when I visualize it, you will see that it's a very nice data set. It has many variables, some scale variables, some vector variables, and it's just a very nice data set for demo purposes. So let me load it. And before I hit apply, so it's not loaded yet, I will make sure I click the checkbox that says Hadi Global. So it's a scalar variable, has a very strange name. I have no idea what it stands for, Hadi Global, but it's just a name for a variable, three-dimensional scalar variable. And then, so I'll make sure to load it, and then I hit apply, and the data set will be loaded. So hopefully you can see it without delay on your screen. And then, so what I'm looking at now is just the outline of the entire computational box containing my three-dimensional variable. So I'm going to switch to a surface view. And so the surface view is not so interesting because I'm not showing any variable yet. So I want to color the data set by the variable. So I'm going to change from coloring by solid color to coloring by the Hadi global variable. And so here's my distribution. I'm looking just the outer surface of the data set. Obviously, there's data defined not just on the outer surface, but inside as well. So I can do lots of things to visualize data inside. For example, I can do a slice, or I can do a clip filter. So let me do the clip filter. So I'll apply clip filter, which dissects the data set in two, throws away one half of the data set, and then keeps the other half. And it's a very easy way to show a two-dimensional slice while keeping the three-dimensional nature of the data set. So I can actually drag the normal vector to the cross-section, to the clip plane. And then once I'm satisfied with the direction of the normal vector, I can drag the position of the plane along that direction. So I'll say here, I'll say apply. And it cut my data set in two, throwing away one half and keeping the other half. And I can actually see, I can see what's inside this data set. So there are literally more than 100 filters. There are some 130, 140 filters built into Triview. The ones that you can apply in this context are not visible in gray, and the ones that you cannot apply in this context are visible in light gray color versus the dark gray color. So clip is just one of the filters that comes by default with Triview. So let me try a different view. Let me go click on the original data set here in the pipeline browser, and let me try to do a couple of isosurfaces. So I introduce an isosurface contour filter, and let me draw two isosurfaces, one at 2, value of 2. So notice that the variable goes from roughly 1 to roughly 6. So I'm going to draw an isosurface at the value of 2, and then the second isosurface at the value of 3. Okay, so hit apply, and here are my couple of isosurfaces. So you can see that I have two layers now. I have the original clip view and then the contour or the isosurface view. So I'm going to hide the clip. I'm going to look at the isosurfaces only, and because they're colored by solid color, so I want to see which value is which. I'm going to switch to coloring by the variable, and actually I don't see the variable here because I need to make sure that I say compute scalar, so the actual value of the variable is passed through the filter. So hit apply, and then let's color by the variable. So you see that there are two values. So the isosurface at the value of 2, as you can see here in the color map legend, and an isosurface at the value of 3. Right? And you can actually make them transparent, and there are lots and lots of things you can do. So pretty much anything you can think of, you can do fairly easily in Triview. So let's make them semi-transparent. Let's bring the previous clip view. So here it is, and let's make it also semi-transparent. So something like this. Right? So as you can see, you can very easily do fairly complex visualizations interactively. Right? So what I'm going to do next, I'm going to delete this visualization, and I'm going to load, based on the same data set, I'm going to load a slightly more complex visualization, which is saved in a state file. So a state file basically lets you save the full state of your visualization. So in case you want to reproduce it later, or just save it as a backup in case Triview crashes. So both Visit and Triview crash once in a while when they run into internal bugs or have some problems with the operating system. So I erased everything, and I'll go to File, Load State, and then I'll navigate to pre-saved state file, this one. So it's exactly the same data set, except that now I'm visualizing two variables. One of them is the original scale variable, hide global. The other one is a variable called grad, and it's just a vector field, a velocity field. And so let me see. It usually takes a few seconds to visualize it in Triview. So, okay. You should be able to see it now. And as you can see, it's a fairly complex visualization where I'm showing two fields, but both fields are colored by the same variable. Both of them are colored by the hide global variable, so a scalar three-dimensional variable. And I'm visualizing the first variable as a clip. You see semi-transparent clip here at the bottom. And then, so here I have just the clip. And then here I have the tube. So the idea here, I have a vector field that is passed through a stream tracer filter to visualize it as streamlines. So something like this. Right? And then I pass the output, I take the output from the stream tracer filter, and I use it as input to the tube filter to make the streamlines thicker. And you can actually modify all the properties of each of these objects in the pipeline browser. For example, I can modify I can make the tubes thicker by simply clicking on the tube here, and then here are the properties of the tube filter. So let's make them thicker by modifying the radius. So hit on apply. I'll take a couple of seconds to compute it, maybe 5 seconds. Okay, And as you can see now, the tubes are thicker. And everything is interactive, so you can actually modify all these properties interactively through these dialogs. So now what I will do, I will try to animate these visualization. I will use the built-in Python shell. So I'm gonna go to Tools, Python shell, and this will open another window into which I'm gonna paste a Python code. So I have a predefined Python code that does rotation. So let me just paste it. And while it's running, you can see that the visualization is spinning. I'll go slowly through, well, I'll go through the code. So what it does, it takes the current state of my visualization, the first line, that it records all the properties of the camera. So basically things like how far you are from the visualization, the angle, the opening angle, and the position of the camera, and so on. So I set up the first frame and the last frame. So the first frame is 0, last frame is 45. So basically I organize a loop between, it finished. I organize a loop between 0 and 45. And at each loop iteration, I rotate the camera position by 1 degree azimuthally. And then, well, actually, I rotate the camera position, but the position of my object that I'm visualizing relative to the camera by 1 degree. And then I save the resulting image as in the current directory as a PNG file. And so if I look at, so the script already ran, it took something like 20 to 30 seconds for it to run to do 45 or 46 renderings, static images. And then if I go to, so here I have the output, 45 PNG files from 0 to 44. And what I'm going to do now, I'm going to use FFmpeg, which is a beautiful open source command line utility for working with movies, for working with animation. I'm going to stitch these 45 frames into an MPEG, a QuickTime compatible MPEG for movie. So I'm going to copy and paste this command, and it's doing processing. So it created a movie, which is only 659 kilobytes, so very efficient compression. And let me play it back for you. So I'll just open the movie I just created. And here it is. So this is the visualization we just created with an interactive Python shell in Triview. So let me play it back. So hopefully it plays nicely. If it doesn't play nicely, then let me know after the webinar, and I'll be more than happy to send you the script that I used to visualize this, to produce this animation. So in Triview, there are several different ways of doing animation. So this is one of the ways, by simply writing your own Python script. What you can also do is you can use the built-in ability to visualize of Triview to visualize any property of any pipeline object. So I'm going to show you a demo now. Let's go back to, let's show the clip again. So here we have the clip, and let's animate the position of the clip, moving the clip plane from bottom to top. So what I'm going to do now, I'm going to click on View, bring up an animation panel, and here we have the clip. And one of the properties is origin. So I'm going to look at origin 0 because I know that the x coordinate is the vertical coordinate right here. So that's the one I'm going to do animation in. And so I click on plus, that introduces a new timeline. I double click on it, and then so we're going to change the position from -10 to 10. And the only other thing I'm going to modify is number of frames. I want to have a fairly large number of frames so that it doesn't play instantaneously. So 100 frames. And then what I'm going to do now, I'll close this so my visualization is a little bit bigger. I'm going to hit the playback button. And as you can see, it plays quite nicely. So at least it plays nicely on my screen. Hopefully you can see it as animation on your, in your video. And it just does a nice visualization. And if you want to save it, you can go to File, Save Animation, and then we'll ask you which form you want to save it, what resolution you want to save it, and just go through the dialog, and you will have a nice animation stored on the disk. And as you can see, it's very, very easy to produce animation based on a property of a pipeline object. So just click on any of the objects, and things like direction, the position of the clip plane, color, opacity, pretty much anything you can think of, any property of this visualization, you can use it as an animation variable. Okay. So I'm going to take the questions at the very end of this presentation. I'm going to now switch to Visit, and I'm going to run a couple of demos using the same data set. So let me actually, I'm going to pause this. I will quit Triview, and I will start Visit, and we'll try to run a couple of demos. Okay, so I have Visit running locally on my laptop. The interface is very, very different from Triview. So that's why people who are used to using one of them have difficult time trying to switch to the other one, because the interface is very different. But in terms of capabilities, Visit and Triview are very, very similar to each other. I mean, they've both been written with a goal of visualizing very large data sets in parallel, and they have these they have this architecture, how should I say it, multi-piece architecture, where you have separate clients and server. And when I run Visit Triview on my laptop, both the client and the server are run as part of the same application. But I can also start a client locally and run the server, either Triview or Visit server, remotely, and then connect the two. And then all heavy rendering, data processing, and all data rendering visualization will be done by the remote server, whereas all GUI, all results are seen on my local laptop. All right, so right now I'm just running everything, both the client and the server, as a single application. So I'm going to load the data set, exactly same data set. So it's stored in documents, this directory, and then it's called noise.silo right here. So let me load it. And then I will add a pseudo color plot, basically a color plot of the Hardy global variable. And then I will draw it. Again, here we have the same three-dimensional plot. I can make it semi-transparent by double-clicking on this and change the opacity to constant. And let's just change to something like this. Apply. Okay, you can see that it's semi-transparent. It's a three-dimensional visualization. Let's draw an isosurface, a couple of isosurfaces. We'll introduce an operator. So let's see. We're doing a. Actually, let me add a contour plot. Sorry, add a contour plot of Hardy Global, and then click on Draw. So here we have lots of contour levels, and if I double click on this, I can actually specify how many levels I have. Let's have also 2 levels. So number of levels is going to be 2. Hit the Apply button, and so here we have 2 levels. Now let's make them semi-transparent so we can actually see through them. So here we go. Apply. Dismiss, and let me hide the first few, and so that I'm looking only at the isosurfaces. And as you can see, it's really very powerful, very similar to Triview. It's just the interface is very different. So let me now try to run a Python script written in Visit Python. So what I'm going to do, there are a couple of options here. You can go to controls and either open the command line interface or the where it says Launch CLI, stands for Command Line Interface, or you can click on Command. I'm going to do that, and it will open a browser into which I pasted a Python code. And so I will run this Python code and pay attention to what's happening in the visualization window. So hopefully you can see the visualization window right here. So as I'm running this script, my visualization will actually I will fly. Well, in this case, I'm flying away from the visualization, so that's not what I wanted to do, but I guess I rotated my visualization. Actually, let me stop it. Let me reload. What I'm going to do, I will reload. I will play this animation not for this view. So let me actually erase everything, or all visualizations, and let me preload a state file with a more complex visualization, and then I'll play it back. So I'll go to File, Restore Session, and then I will go into the same directory, and I will load this file. So this is just a warning. And as you can see, this is a visualization very similar to what I have done before with the state file in Triview, showing a clip filter and a three-dimensional rendering of the velocity field with tubes, with a stream tracer. And you can actually see here in the pipeline browser on the left how this visualization was done exactly. So there's a Hardy global variable that is that passed through the clip filter and then visualizes pseudo color, basically as a color plot. And then a second visualization where I take the grad variable and pass it through the integral curve filter. So that's an equivalent of stream tracing in Triview, and then pass it through another tube filter and then visualize it as a color plot. So this is for the stream tracer lines. And so now let me open again the command window, and then let me play it back. So I say execute and then see what happens. Actually, the same effect. So I guess I screwed up slightly with the camera position. But the idea here is you can actually animate very easily things from the Python script. Not exactly the effect I was going for, but I guess we'll have to do it because we don't have a lot of time left in this presentation. So similar to Triview in Visit, you can animate pretty much anything. So any type of, any property you can think of, you can animate it fairly easily. So now let me close this instance and go back to my slides. So my slides are here. Let's talk a little bit about remote visualization. So if you have data sitting on one of the clusters, let's say cluster with some name at .consortium.ca, then you have quite a few options on how to visualize this data. So if your data set is very small, then you can simply download to your local machine, to your laptop, and visualize it locally. But obviously, if it's multiple gigabyte data set, then you'll run into problems trying to visualize it locally on your laptop, simply because you'll run out of memory. Then what you can do is you can visualize it remotely on the cluster. So the easiest option is to log into the cluster using SSH-X command. So -X does X11 forwarding, so X Windows forwarding. And what we'll do is if you have an X11 server installed on your machine, so usually these are installed by default on a Mac and the Linux machine. If you're on a Windows laptop, then you can install it as a separate download. And then when you open, so once you connect it to the remote machine via SSH-X, you can open a window on the remote machine and it will be displayed locally on your machine. And you can actually interact, you can work with a remote Triview client or a remote visit client interactively. The problem with this method is that it's very slow. So X11 forwarding has been around for about 30 years and has been designed with much simpler applications in mind, not with such heavy graphics duty applications such as Triview and Visit. So if you try this approach, it will work, but it'll just be very slow, not exactly interactive. So much better approach is to start a remote desktop client on the cluster. It could be a VNC client, an X2Go client, so these are different applications. So most consortia run VNC, remote, not VNC, not client, VNC server. So most consortia use VNC, Calcul Quebec uses X2Go. And the idea here is that you will start a VNC or an X2Go server on the remote machine. Then you start a similar, an equivalent client on your laptop, and then you connect the two. And then you'll get a remote desktop where you can actually start Visit or Triview, and then these will be run remotely on a cluster, but you will have a local window as well in a local copy of, local view of the remote desktop, and you can actually work interactively. And it's much better approach. It works much faster than the SSH-X approach, and it'll be much more pleasant to use. So there's also an option. I mentioned before that both Visit and Triview have architecture where you can run a separate client and a separate server on different machines. So you can start a client on your laptop, you can start a server on the remote machine, on the cluster, and you can connect the two, and then you can visualize things very nicely without transferring any data to your laptop. And then finally, if you already, so this is everything I've said before is for interactive visualization, where you want to have a client and you want to have an interactive view with mouse buttons and menu items and so on, and work with your visualization interactively. If you already wrote a Python script that does all visualization for you, if you want to just run the Python script without any interactivity, then a far better approach will be to simply run the Python script as a batch job on the cluster, and there are many ways of doing that. So you can start either shell as part of a compute job on a compute node, or a scheduled job on a compute node, or you can simply submit it as a regular compute job, and you submit it, it runs a few hours later, a few days later, and at the end of this job you have a nice visualization. And it's very easy, fairly easy to do this. So if you have any questions, please let me know. We have also in WestGrid, we have fairly detailed pages on our website describing how to do that. So let's see, how am I doing with time? So I was hoping to run an interactive demo of remote visualization, but I think I will not do it now because we have only 15 minutes left, and there's still quite a lot of material that I wanna cover. So I'm gonna skip these two slides. They show exactly what you should do, all the steps you need to take if you wanna run either Triview or Visit on the WestGrid cluster called Parallel. Parallel is the name of the cluster. So it's parallel.westgrid.ca. You need a special account on this cluster, so not just usual WestGrid account, but you have to ask us, and so if you need to use the cluster for either, for GPU capability or for some other reason, we'll give you an account. It's free, you just need to ask us. And basically, this cluster has 160 or something like that, 165, can't remember the exact number, GPU cards on special interactive nodes. And the idea is that you can schedule a job on one of these interactive nodes. And as long as you specify tell the scheduler using this format, so -q interactive -I, that you want to use a GPU node, then it will start an interactive job on one of the GPU compute nodes, and then you'll have to start a VNC server by hand on the compute node. Then you start a VNC client on your laptop. Then you'll need to organize SSH port forwarding between the local port, VNC port, and the remote port on the compute node running the VNC server using this command. It's fairly easy to do. So it sounds complex, but it's fairly easy to do. Just I don't have enough time to show it now live. And then you start a VNC server on your laptop pointing to the local VNC port. It'll open a remote desktop where you can simply start Visit and Triview and work with a remote copy of that visualization package as if you were running it locally. So it's fairly easy to do. And when you run a Triview Visit remotely and you open, go to File, Open Dataset, it will give you a dialog where you will see the remote file system on the cluster, not the file system on your laptop. All right. And then, so a very important note is that if you have a data set that is sitting on a cluster that does not have any GPU cards, and most of our clusters don't have GPU cards, then what do you do? So fortunately, you can actually run both Triview and Visit without any GPUs at all. You can run them purely on CPUs. And so as I mentioned before, there are a number of software-based, so CPU-based rasterizers or ray tracers. You can use both inside Visit and Triview. And depending on which rasterizer or ray tracer you picked, it will be fairly slow, or it will be fairly fast. So there are a couple of really nice libraries from Intel. One is called OpenSWR. OpenSWR is an open source software-based replacement for OpenGL. And another is called Osprey, which is an open source ray tracer from Intel. And both of them are implemented in both Visit and Triview. So you can actually do, heavy-duty rendering on CPUs without any GPU at all. And again, if you want more details, we have some details on our webpage. We also have, so I'm going to talk about webinars in a few minutes, and one of the previous webinars in September was on how to use Osprey inside Triview and how to do it both locally and remotely. All right, so across the country, so far I talked only about remote visualization in WestGrid. So if you are from Ontario, from Quebec, or from the Maritime provinces, so each consortium has its own setup for visualization. I'm just going to talk briefly about SciNet, SharkNet, and Calcul Quebec. So in SciNet, the main machine is GPC, and on GPC they have both. You can run visualization on CPU nodes or GPU nodes. So they have one or two interactive visualization nodes with GPU cards, and they have the regular GPC head nodes without any GPUs. So on both types of nodes, you can actually start a VNC server, and then you will start a VNC client on your laptop, and you can organize, so do SSH port forwarding using exactly the same syntax I showed on the previous slides. And so the setup is exactly the same as on the WestGrid parallel cluster, except that you don't even have to start a job. So you basically log into GPC and start a VNC server on either a visualization node or on the head node, and then connect the local client on the laptop, and you're good to go. So no, you don't have to wait for an interactive job to start, unlike on the parallel cluster. So SharkNet, also in Ontario, has in my opinion, the best setup of all consortia. So what they do, they have a number of, first of all, they have a number of visualization workstations that you can log in directly, well, remotely. And also they have a fairly beefy server, which is called VDI. And it's meant for interactive use, including visualization. And they have a number of Linux containers, so different versions of Linux, CentOS, Fedora 20, and Fedora 23. And basically, you'll connect to these, and you'll get a remote desktop. And these machines, so VDI server is connected. So it has several. It has two key graphics boards. Each graphics board has 4 GPUs, and these GPUs can be even shared. So a single GPU can actually be shared among multiple users. And this is, so GPU sharing is done by virtual GL. And They also have a nice interface through the web browser. So if you go to sharknet.c, the web address is right here. If you scroll down to the visualization station, so to the VDI containers, and there will be a blue icon, which you can click, and it will give you a remote desktop inside your browser. So that's done using HTML5 no VNC. And you can log in, enter your credentials, so SharkNet credentials, username and password, and you'll get immediately a remote desktop inside the web browser. You can rescale it, and then you can actually do everything without even installing a VNC client on your machine. So Callback, as I mentioned, uses X2Go on the Colors cluster. So if you have a large data set on Colors, you can actually start an X2Go client on your laptop. You don't have to download it. It's open source. It's free. And basically, you point the client to the X2Go server on Colors. It's always running. It handles authentication. So click on Connect. It will ask for your Colors username and password, and then you'll get a remote desktop inside which you can start VNC or Triview. All right, so we have two large national systems coming online, hopefully from April. So I'm sure you've heard of them. One is CEDA at SFU, the other one is Graham at University of Waterloo. And both are meant to be, well, replacement essentially for all existing machines. They're much, much bigger. They're much more powerful. So both of them will have close to 30,000 CPU cores and several hundred GPUs. And we'll have some interactive setup, interactive visualization setup on these machines. So the details are yet to be determined. So things like whether you'll be able to access the visualization nodes directly from the outside, or you have to go through a head node, or you have to access them through the job schedule in the head node. So these details are yet to be determined. We're working on this, but basically as soon as the classes come online, we'll have some interactive visualization setup. And you'll also be able to run batch mode visualizations, as I mentioned before, on pretty much any node. So whether it's a GPU node or regular compute node without GPUs, if you already wrote a Python script with a Triview or Visit visualization, and you can simply submit that script to the batch job, and then it will run, let's say, overnight, and you wake up in the morning, will have very nice visualization. All right, and the full details on how to do visualization on the new systems, of course, we'll provide a lot of documentation on on our wiki that I have the link in the second slide in a few months once the systems are online. So finally, I'm going to talk for a few minutes about training, and then I open the floor for questions and comments. So we have two types of training. So first of all, in WestGrid, we're running full-day workshops that I'm responsible for. So I joined WestGrid 2.5 years ago, and since then we run 14 full-day in-person workshops. So I travel to various WestGrid institutions, and I give these full-day workshops. We have online, they're free, you don't have to pay anything. So you have to register. Well, we encourage people to register, so we have a rough idea of how many people will attend in advance. So there are 3 workshops coming up very soon, in the next month or so. On February 1st, we have a full-day workshop at SFU downtown campus. That's the Harbor Center campus, and it's going to be on visualization. So February 1st, we have an online registration page. If you want to register, go to westgrid.ce and then click on the events, and we'll have a link for this workshop, And then we have another visit workshop at the University of Alberta in Edmonton on February 28th. And then very likely sometime in early March, we'll have a workshop at the University of Calgary. So watch our events page, and you will see the links and full description of all full details for these workshops there. So if you want to have either a Triview or a visit workshop at your location, your institution, please let me know. I'll be more than happy to travel to your institution as long as it's inside WestGrid, and then I'll present a full training on site. So we also run webinars. So this webinar is part of this webinar series on visualization. Our visualization webinars happen once every 2 months, bi-monthly, in January, March, May, September, and November. And usually for these, we choose very specific topics. So this is the very first webinar where we have just a general introduction to visualization and visualization support. But usually we'll try to cover more specific topics. And so far, so previous to this webinar, I give 5 webinars on very, very specific topics. So batch visualization, graph network visualization with GAFI in 2D, 3-dimensional graph visualization with Network X, VTK, and Triview, CPU-based rendering last September with Osprey, and then in November I talked about scripting and other advanced topics in visit visualization. So all of these are recorded. The video is recorded, so you can actually go back to our archive and view them. And also we have the slides available for download for free. So we're planning now the next round of our webinars starting. So the next one is going to be in March. And would like to get some feedback from you, from the research community, on what exactly we should cover in these webinars. So I will cover roughly 20 or so topics in the next few slides, just to give you an idea of what sort of things we can talk about. But if you want to see a presentation on something else related to visualization, then please let us know. So you can actually to leave your feedback, you can simply email to info@westgrid.c, and this email address is monitored, this mailbox is monitored right now by Jana. She will read your question or your comment live in the next, in a few minutes. You can also mouse over your presentation if you're using a video client. If you mouse over right now, you will see a bunch of icons, and the second icon opens the chat window. You can type your question there, or you can simply will open the microphone for questions in a few minutes, and you can just use audio if you have a microphone. Just unmute yourself, or at any time in the future, just send me a direct email. So here are some ideas that we're thinking about. So one of them is more advanced topics in visit scripting. So I ran a quick demo half an hour ago showing what visit is capable of, but there's certainly a lot more I can talk about. So one of the topics is callback functions. So the idea here is that when you're running visit, I showed you the example before. I was running the graphical interface where I had the visualization window, and then I was running the Python shell at the same, or Python editor at the same time. So when I was click on the execute button, the Python script ran, and then it asked the GUI the GUI client to do something, basically to run the script and to render whatever commands I was asking it to run. And you can also, so you have feedback from the Python shell to the GUI, but you can also have the opposite connection. So you can have things happen in the visit GUI, and then you can write Python code in Visit Python to act on that. So, for example, you can click on various parts of your visualization, and at the points where you click on, you can just pick up some values of your variable, or perhaps multiple variables at these points, and then run some script based on that. Or you can program the time slider in the GUI to do something else. So, for example, if you have a time-dependent simulation, and interesting things happen in different parts of the volume at different times, you can actually program your GUI client to feed information back into a script in such a way that when you use the time slider to jump to different times in your simulation, different parts of the volume will be displayed automatically. So that's called callback functions. The other topic is how to display multi-resolution. So I'm thinking about AMR, adaptive mesh refinement, either box structured or cell structured. How we can display these multi-resolution data sets in Triview and Visit. So both Triview and Visit have very rich capabilities for displaying AMR multi-resolution data sets. Also, you can also visualize volumetric multi-resolution data sets, AMR data sets, with a special tool called YT, which I have no idea what it stands for, but there is an online page you can click on, ytproject.org. And this tool is really, really good for visualizing AMR dataset, multi-resolution datasets. It was originally written with astrophysical datasets, galaxy formation models in mind, but it's actually used now by people in the medical imaging community, MII, in the geophysics community quite a lot, and it's really a wonderful tool. So it's not exactly interactive, it's more of a Python library. You will run Python scripts, but it's really, really fantastic. Produces very nice, very impressive visualizations. So of course, visualizations on the new systems in a few months, we're going to cover that. Distributed in parallel, distributed memory visualization with both Triview and Visit on the clusters. Client server, details of client server setup, how to do client server visualization, both Triview and Visit. Working with VTK objects in Triview and Visit. So the idea here is that I didn't have time to talk about this, but you can use what is called a calculator filter in Triview, which will basically let you process your variables somehow, in some way. So for example, you can take, I don't know, a density field and a density variable and a temperature variable and calculate a new variable called pressure, which is going to be product of density and temperature, and visualize pressure, or introduce some other new variable. But all these calculations are done on existing variables, and they are done on existing discretizations. So with the calculator filter, you cannot modify your discretization. So why you would want to modify discretization? So let's say I have three-dimensional data set, three-dimensional grid, and you want to project the grid onto some other surface. So to do that, you have to modify the underlying discretization, and with the calculator filter, you cannot do that. So fortunately, in both Preview and Visit, in more advanced scripting options, there are more advanced scripting options that will let you work with discretizations and VDK objects directly, that will let you modify the underlying discretization behind some variable. All right, so working with NumPy arrays in Preview and Visit. So normally all two-dimensional, three-dimensional data sets in Preview and Visit are stored not as NumPy arrays, but as VTK objects. But you can actually feed this data from VTK, convert them from VTK into NumPy. And so the advantage of NumPy is very popular, numerical library in Python for working with three-dimensional, two-dimensional, well, four-dimensional arrays. And you can actually access it from inside Preview's or Visit's Python. You just have to know how to do this. So rendering on newer CPUs with Intel's Open SWA library, which I mentioned before, so that's rendering without a GPU. Writing custom reader plugins in Preview and Visit. Preview Web. So Preview Web, the idea is it's a framework for building websites. So basically, it's a JavaScript library for building a website that will talk to a remote Preview server. And the idea is that you can actually put your very large data set online, well, somewhere on a server that will run Preview. And have an HTML page somewhere online on a web server that will talk to the Preview server. And basically, people will be able to do some fairly simplistic, not exactly full capability of Preview, but fairly simplistic visualization, which nevertheless will let you put your data sets online, and basically will open your data sets for interactive, use and visualization for to the research community. So Preview Cinema, the idea here is that if you have a very large data set, then it might take a very long time to render all frames of this data set, and you can pre-render these frames and then run these pre-rendered images inside the Cinema program, and that will give you sort of interactive-like rendering, except that it's not interactive rendering. So it's going to be interactive in the sense that you'll be able to do things, turn on different on and off different variables, switch to different views, rotate, spin, zoom, your data sets zoom in, zoom out, and things like that. But it's all going to be not rendered live, but with pre-rendered images. So this is useful if your data set is so large that rendering takes a long time, and essentially interactive rendering is not interactive anymore because each frame takes so long to render, let's say many seconds or several minutes. So in that case, you can use Cinema for visualizing interactive visualization of pre-rendered images. In-studio visualization in both Preview and Visit, already talked about that at the beginning of this presentation. Programming custom UIs in Visit. If for some reason you want to do that, if you don't like the default UI client in Visit, you can certainly write your own client, and it's fairly difficult to do that. Well, I mean, it's not difficult, but it's quite a lot of effort, and in my opinion, it's not totally useful because what it will give you, it will simply give you a simpler interface that you or other, let's say, members of your research group can use, but it won't give you any capability beyond what you already have in Visit. It will just give you a simpler, custom interface. That's all. So last slide. Simpler two-dimensional libraries like Matplotlib, Seaborn, Plotly, Bokeh, what have you. So why not? As I mentioned before, we can help you with these libraries. It's fairly easy to use this. So I don't envision a lot of requests for help using these libraries, but if for some reason you're interested in a webinar on a specific library, two-dimensional library, please let us know and we'll follow up. So 16 constructive solid geometry meshes in Visit, or general unstructured, let's say Voronoi or Delaunay, whatever, meshes in Preview or Visit. 17 photogrammetric processing of images. So photogrammetric processing of images refers to if you take a whole bunch of images, let's say from different angles of, I don't know, an artifact or of a building, you can actually stitch these images together and build a three-dimensional model that can later import into any number of tools, including Visit and Preview. And so again, if you're interested in photogrammetry, then please tell us exactly what you need is, what you want to do. And so the problem with photogrammetry, there are very few, almost no really good open source tools. So there are open source research projects on photogrammetry, but they tend to be short-lived. So it's very difficult to actually support them and to use these packages. There are a few, but they're not very well supported. And then there are a number of really good commercial but very expensive packages. And in general don't support commercial packages, well, simply because they are expensive. So I personally have reservations about recommending really expensive commercial software to users. But if for some reason you're interested in photogrammetry, please let us know what exactly you're interested in, and we'll try to find an open source solution for your need. Visualization of point cloud data, so that's LiDAR images. Interactive online visualizations for portals, and any other topic to your liking. So that's all I have. We are past the hour, so I'm going to open the floor to questions. If you have a question that you want to ask via audio, please unmute your microphone, and I'll stick for another 10-15 minutes, and I'll be happy to answer them.
Thanks, Alex. I'll jump in first, just because we did receive a question via email. Aaron typed it in the chat window there, but I'll just read it for you. So we had someone watching via the web stream, and they had a question about one of your slides earlier where you were showing how the images were created by the Python script in Triview, but he missed how the images were stitched together in the command line. So
yes.
He was wondering if you could repeat that step with the name of the package that was used.
Okay. Does the web stream have access to the chat window? Can I just paste it into the chat window, or they don't?
They don't, but if you paste it, I can email that back to them.
Okay, sure. I will do it now. Let me just copy and paste it. Let's see. So here is the command line ffmpeg command. Let me just open the chat window that I used. And the nice thing about this command is that it will work both in Linux and macOS if you have ffmpeg installed. So for example, we have ffmpeg installed on the parallel cluster in the WestGrid, and this exact command should work. So the only caveat here is, so you specify -R10 says that you're building a movie with 10 frames per second, and then -I followed by frame.png. So that's the pattern of the input files you're looking for. So your input files have to be named that, well, something like that. So starting with frame ending with .png, and then $04D means that you are looking for 4 digits starting from 0000 to whatever number, and it'll just scan these sequentially, and then it'll convert these frames into a movie. And the output name of the movie is going to be spin.mpeg4.
Great, thank you. If anyone else has a question, please feel free to unmute your microphone, and you can ask it now.
So most importantly, I'd like some suggestions and well, to have feedback on the future topics of the webinars, because I can essentially pick up any topic I want, I'm interested in, but the question is whether this is relevant to what you do. So if you have some special needs, if you have a data set you want to visualize, if you're interested in a particular topic, please by all means let us know. Send us an email or send an email to me and let us know, because essentially you can tell us what you're interested in, and we'll try to follow up.
We'll also be sending out an evaluation form just shortly after with a link to Alex's slides. So I'll include his options there, and you can vote on which ones you would like. And again, feel free to suggest any additional ideas that weren't listed today that you might be interested in. So we'll send a copy of the slides after this session with an opportunity to vote on future ideas. And then, as mentioned earlier, we have recorded this session, so I will send everyone who registered a link to that archive recording in case there's anything you'd like to go back to and refer. It will take about 1 to 2 business days for that recording to be posted online, and we'll be posting that to the WestGrid website.
Any last question?
Nope, nothing.
Not, then thank you very much for watching, and looking forward to getting some feedback. Thank you.
Great. Thanks very much, Alex.